Okay, students, let's dive into chapter 15. Looking at traveling waves and sound, the wave model. Now, in order to understand matter waves or mechanical waves and sound waves, we need to understand that there are basic properties to how waves behave, and of course we have to look at those basic properties, and you'll see what I'm talking about as we get into the chapter. For example, just to give you an example, the linear mass density of a string if it's a matter wave, and then of course the frequency and the period of the wave, all those come into play, and we've already discussed these in chapter 14. So we look at mechanical waves. Now, in order to have a mechanical wave, they must have, I forget to do that. You must have a medium, okay, in order for it to be a mechanical wave. So you've got to have a medium, all right? And here they use water. Water is always a good way to demonstrate waves. For one thing, it's very common, very cheap. And we can see when we apply energy to the water by, for example, throwing a stone in, give the drop, that's basically saying we are applying energy to it from the weight of the stone colliding with the surface of the water, which of course it has energy in joules. So we see this energy transferred now through the water as a wave. So we have a medium, which is the water. Then the disturbance is the wave that passes through the medium, okay, which displaces the atoms that make it up, okay? So what's the difference in the medium and what is the difference in the disturbance? Well, the medium is the material, and the disturbance is the actual wave that is displacing matter, okay? In other words, you could actually call the disturbance, I'm going to use this kind of loosely, the energy of the wave, okay? So you have a wave, of course you have to have in order to have a disturbance, you got to have a source. In this case, it looks like someone threw a rock in a pond, okay? Now, just like with linear motion, just like with Newtonian physics, the same applies here. The wave will have a speed, okay? Now, the unique thing about a wave, you've got to understand something, that the medium as a whole doesn't travel. Now, you're saying, well, that doesn't make any sense. Well, it doesn't, okay? It really doesn't travel. It's the energy that's being transferred, okay? All right? So you got to realize that it's a transfer of energy, not a transfer necessarily of matter, okay? And you say, well, then how in the world does a wave do so much destruction? Well, if you have a lot of energy in the wave, then guess what? The wave has to compensate the energy. And so if you have a lot of energy in a wave, then guess what? The water actually piles up on itself. It has to, because of the energy. Energy is going to be conserved. So you're actually transferring energy, but it's not really transferring material or substance outward from the source, okay? So in other words, if I throw the rock in here, guess what? The water just don't go and fly away, and leave a big hole there. No. Okay, it's just a transfer of the energy, okay? And that makes sense if you'll think about it in those kinds of terms. When you throw a rock in a pond, well, does it leave a big hole in the water? Well, no. Well, okay then. It's a transfer of energy. All right, so what about electromagnetic waves? Now, electromagnetic waves are waves that do not require a medium. Now, can they travel through a medium? Well, sure they can, okay? Sure, light can pass through water, pass through air. Sure it can, okay? Electrical sparks can, but you don't have to have a medium. It actually can pass through a vacuum. The energy that comes to us from the sun is through the vacuum of space. There is no air out there, okay? But it gets to us in what form? Of course, it's electromagnetic. Now, what matter waves, of course, are those that describe the wave-like characteristics of material particles such as electrons and atoms, okay? So when we talk about matter waves, so we're talking about the behavior and the characteristics of electrons, okay? And atoms too. Now, most waves will fall into one of two categories, either transverse or longitudinal. Here's a good example of a transverse wave. And you say, well, how do you know the difference? Well, with a transverse wave, the medium moves perpendicular to the direction, okay? So you got the medium, notice it's moving this way to the direction of movement. Okay, so the medium is up, and that is a right angle there. It's perpendicular to the direction it's moving. That's how you know it's a transverse wave. You pop a rope, pop an extension cord. You see that little camel hump go down the rope or the extension cord. That is a transverse wave. What about longitudinal waves? Longitudinal waves, they move back and forth. It's like a push or pull here on a spring. If you've ever taken a slinky and stretched it out on a desktop, and then you pull one of the little springs, parts of the slinky back, and then release it, well, you see that rarefaction and compression, which I'm getting a little ahead of myself. And so what are we saying? The medium moves parallel to the direction of the wave, okay? So please know the difference in those two. Now, here, some of the most common examples of transverse and compressional waves, or longitudinal waves, by the way, we call longitudinal compressional waves too, is, of course, earthquakes. Now, when we look at earthquakes, we actually have three types. There's P waves, S waves, and L waves. L waves are surface waves, much like what you see on the ocean, but we're not going to talk about those here. We see the P wave. The P wave actually moves faster than the S wave. The P wave is your longitudinal now. P waves are longitudinal, all right? And your S waves are transverse. Now, they tell you here, the P waves are faster, but the S waves are more destructive. So notice you see the S wave, that is a transverse wave, okay? So you see it looks kind of like the waves on the ocean, doesn't it, okay? All right, so you got P waves and S waves. So that's a good example of transverse and longitudinal or compressional waves. Now, what about waves on a spring? Well, if you actually analyze a particular segment of a string or a rope when you pop it, you will notice that, of course, there's tension along the rope, and there's a net force in this direction. You say, how do you know there's a net force in this direction? Well, okay, how do you get that hump? You know, where does the hump come from, okay? You know, how does it work if there's not a net force, you wouldn't have the hump, okay? So if you analyze this and break it down and start plugging in Newton's laws, we see that as this pulse now travels along this wave, and they're calling that the pulse, okay? That particular segment of string, as it moves, we see, of course, it's a transverse wave, and once it's started, it will continue until it will continue to move because of its internal dynamics of the medium, okay? Now, what about sound waves? Well, and we're going to come back to that string here in a little bit. What about sound waves? Well, of course, when you turn the speakers on, you don't have transverse waves. You have waves that come out longitudinally. And basically what you have is a compression of air. That's really what a sound wave is. And you have right here what is called a compression, and these regions right here are called the rarefaction, okay? Compressions and rarefactions. All right, now, so in order to understand the wave speed in a medium, okay, notice it doesn't depend on the size and shape of the pulse, but how the pulse was generated or how far it has traveled. So notice it doesn't depend on the size and shape. It depends on what? It depends on how it's generated and how far it's traveled. Notice that, very, very important. So in order to be able to calculate this, we got to understand this quantity right here, and this is called the linear density of the string. Okay, now we're talking about a motion through a transverse motion through a string or rope or extension cord, something like cable, chain, whatever. Okay, this is called the linear density. It's also referred to as the linear mass density, and we use the Greek letter mu, and of course it's the mass in kilograms divided by what? The length in meters. You know it's got to be kilograms and meters, as it is in most all cases in physics because of the SI units. And so how do we find then the actual velocity of the velocity or the speed of a wave on a stretched string, okay, or rope or extension cord? Well, notice we have to do what? We take the square root of the tension divided by the linear mass density. Now, we could get into derivations of how we do this and look at the tension and then look at Newton's law, and we come to this conclusion, but we're not going to get into all that, but that's how we come about this equation. All right, and so we have the square root of the tension, and that's tension now, tension divided by the linear mass density, and you wind up with meters per second, okay? Because this, of course, tension is in kilograms meters per second, and meters per second squared, newtons, and then that is kilograms per meter, and it all winds up being what? it winds up being meters per second, okay? So if we look at sound and we look at the speed of sound, then it changes a little bit. Notice there's two different equations we can use here. We use lambda times Boltzmann's constant times the temperature divided by the mass. Now lambda is a constant that depends on the type of gas you have, and again that's just something you pull from a table. Okay, we call that the lambda constant of the gas. Boltzmann's constant, okay, we've already talked about Boltzmann's constant. And then of course, or maybe that's coming up. We haven't gotten to Boltzmann's constant yet, but it is coming up now. And then of course the the temperature of the gas divided by the mass of the gas. Or we can work it this way and do a little bit of substitution here and say the lambda value for the gas times the gas constant, and we need to use I believe it's 8.31 joules per mole Kelvin, okay, and then times the temperature in Kelvin, and then the molar mass, which will be in kilograms per mole, okay? All right, now, so two different equations we can use to find the speed of sound in a gas at a particular temperature T. Okay, now it's understood that this is a constant more or less. If you have, now it all depends on the temperature, the air temperature. The air temperature is 20 degrees Celsius, then we get 343 meters per second of sound in air, but again that's at 20 degrees Celsius. It changes with temperature. Okay, it depends on the temperature of the gas, so it can go up or it can go down based on the temperature. All right, here they give you some. Notice it's slower at 0. Well, no duh. I mean, come on, y'all. Why would it be slower at 0? Well, because the molecules are not moving as fast. Okay. And the air molecules are not moving as fast. It's more dense. The gas is more dense. If it's more dense, it has more weight, and so forth. Okay. Notice helium. All right. Helium. Boy, it really books through helium, isn't it? Well, helium's extremely light. Ethyl alcohol, and so on. Okay. Notice a diamond. Good grief. 12,000 meters per second. Man, that's crazy. All right. Okay. Now, of course, we've already talked about the speed of light in a vacuum, 3 times 10 to the 8th meters per second. And it does slow down in air, but it's close enough to that we can use it, okay? All right, now when we start looking at what we call snapshot or histographs of a wave, basically what we want to do is we want to analyze the displacement of the pulse on a string through a given time interval, and basically what you can do is you can take it as it moves. We plot the sequence. All right, so we're here at time 1. We're here at time 1. Okay, and then later at time 2, the pulse is at this direction, at this position. So notice right here, you say, well, how can we find the displacement of that pulse if we know the speed and we know the time? Well, we get it from this equation right here, the change in x over the change in time, and solve for delta x. And delta x is the velocity of the wave times the change in time. That's how we can find it, and that's how it's done, okay? And of course this progresses on, and then we get to the final point at time 3, and let's say, well, what was the distance that it traveled from time 1 to time 3? Well, you subtract time 3 minus time 1 times the velocity, and boom, you can find the actual motion of the wave, okay? How far the wave moved, okay? All right, now we can of course plot this dot over a given time interval, and notice how the actual pulse goes from here to here, okay? Eventually at time 4 it's back down to 0, okay? And that's just showing you how we can plot that pulse. Now, when we look at, of course, waves on a string, sometimes we do have simple harmonic motion. Depends on the source and how it's produced, but we can produce simple harmonic motion with sound. And notice here that it's a sinusoidal wave, and of course we know the amplitude is what? The amplitude is from the resting position of the wave to the crest of the wave. That's the amplitude. That's how we define the amplitude. And notice it says the crests have a displacement of A and the troughs have a displacement of negative A. Well, okay, that's what they're trying to get you to see here. This is A, and this right here is negative A, okay? And so, again, we measure the amplitude from the resting position of the wave, or the 0 point of the wave, to the crest or trough. And of course, remember, if we measure the trough, it is negative A, and then we can take this and do some substitution if we want to find the actual time at the y position. In other words, how far does it displace? Okay, what is its y position with respect to its motion linearly. In other words, its y position with its respect to its motion in the x direction. Well, all right, at a given time interval, then we can calculate it by the amplitude of the cosine times what? Or the amplitude times cosine of 2 pi x over lambda, and that's actually called the wave number, okay? X over lambda is what we call a K, or wave number, because these are both in meters, so that cancels out and it becomes what's called the angular wave number, and it's a funky looking K, okay? So when we look at this, since we have displacement, notice the wave is being displaced. Notice we have the wavelength here, which is the distance between adjacent crest or adjacent troughs. You could measure it that way. We have wave speed. We have amplitude. All right, now, excuse me. So at each point in the medium, the oscillation with simple harmonic motion, each point in the medium oscillates with simple harmonic motion as the wave passes. So when you have a sinusoidal wave, it is in simple harmonic motion. If you were to say plot the motion of a pendulum here, okay, well then you would get this type of wave, all right? Now, all right, so we have a given time interval, how long it takes to complete one cycle. We already know what that is, and so when we substitute this into our equation with respect to t, not with respect to x, but with respect to time, we notice the equation is the same. The only thing is here is we substitute this right here in time over time, and we have another constant. Of course, we can also say that the period is 1 over f. We can write it that way too. Okay, and then notice what equation we wind up with. Notice we combine the two, and we wind up with what? Well, it's actually the displacement of a wave traveling to the right with an amplitude A, wavelength lambda, and period t is what? Well, it is what? It is, notice they put y with x to t. Now, in other words, as it's moving linearly during a given time interval, so when we plug these in, notice these cancel out, and what are you left with? You're only left with meters, aren't you? Meters over meters cancels, seconds over seconds cancels, and you're left with meters. Now, how in the world can it be to the right and there's a negative in there, okay? Well, if you think about it, final minus initial, okay? If the final is greater than the initial, then it has to be moving to the right. If you think about displacement, remember when we were doing Newtonian, okay? And we say, okay, we start here at 1 meter, and we're going to come out here to 4 meters, right? Okay, well, what's delta x? Well, delta x is 4 minus 1, which is what? 3 meters, okay? Well, how do you know you're moving to the right? Notice the negative right there. We're moving to the right, okay? In other words, our displacement is greater, okay? In other words, we're moving to the right. That's how we get, that's why that negative's in there. That tells me when I see this wave equation, okay, this wave function equation, or wave function as it's referred to, then I know, hey, that wave is moving to the right, and that's the equation I have to use, okay? And you please make sure you write those down on your formula card, moving to the right, okay? Because guess what? What do you think it's going to look like if it's moving to the left? Well, you're going to put a positive in there, okay? If it's moving to the left, you're going to be positive. It's going to be positive. Okay? Okay. All right. That's very, very important. Okay? So make sure you do that. Make sure you write them down that way. All right. Now, all right. So as we've already known, we can find the velocity of a wave by dividing the distances traveled through the given time interval period. Or if we look at it in terms of frequency, then the velocity of a wave is what? Well, it's the wavelength lambda times the frequency. And you say, how do we get meters per second? Come on, y'all. Lambda's in meters, and frequency is what? Frequency is 1 over s, which is meters per second when you put it together. And that's the relationship between velocity, wavelength, frequency for, please write it on your formula card, sinusoidal waves. Sinusoidal waves. Very important that you understand that, okay? All right, so here's just a summary of the relationship, the fundamental relationship with sinusoidal waves. And again, they have them labeled for each type, okay? And so please make sure you write those on your formula card properly. Now, what about sound waves? We've already talked about a little bit sound waves. Sound waves, again, are compressed air. Did you hear me? In other words, their pressure is involved. And if pressure is involved, we can also have power involved. And so anytime we have a compression of air, we have two parts of that compressed longitudinal wave. We have the compression region, okay, and then we have the rarefaction region, okay? Very important you understand that. Compressions are areas, of high pressure and the areas of low pressure are rarefactions, okay? So this is high. High is compression, okay? And low is rarefaction, okay? All right, so ultrasound waves, of course, have high frequency, which are above our hearing range. And, of course, we use these. Animals can hear sound waves, ultrasound waves that we can't. A lot of times dogs will, and cats and other animals will detect an earthquake before it gets to us because of the particular sound wave that's created that humans cannot hear, okay? All right, now, of course, we use these for ultrasound, for looking at infants before they're born and so forth. All right, now, we've already talked about electromagnetic waves. I don't want to skip over this, but I am. We've talked about the different ranges of wavelengths of violet and red light. We know the visible spectrum. Visible light is in a very narrow band of the electromagnetic spectrum. You should remember this, that red light is right at 700 nanometers and violet light is at 400 nanometers. Long wavelength, very, let's see, if it has a very long wavelength, then it has a very low frequency. It has a very short wavelength, it has a very high frequency. So high frequency, and high frequency, and short lambda down here, right? And then, of course, low frequency and long lambda, right? And this also corresponds to energy too. High frequency, high energy, low frequency, low energy from the photoelectric equation, all right? Now, all right, so we look at energy and intensity. We look at the power of the wave, and we know power is the number of watts per second, joules per second. Joules per second is a watt. And so when we look at circular waves, of course, circular waves and wave fronts. Now, wave fronts are the crest portions of a particular wave, okay? In other words, the highest part of the wave. That would be called the wave front, all right? Now, once you get out away from the actual source, then basically what becomes of the wave is what we call a plane wave, okay? So, for example, if you throw a stone in a pond and you're, I don't know, 30 or 40 feet away, eventually what's going to hit you is the wave or the plane wave, not the actual circular wave, okay? Because you're far enough away from the source to where it's basically coming at you at a right angle. All right, now, so spherical waves move in 3 dimensions. Light and sound are spherical waves, okay? They talk about the waves with 3-dimensional ripples, talk about here like on a pond. But once you get on out away from the source, then it becomes what is called a plane wave, And so how can we find the intensity then of a particular sound? Well, we take this and we take the power of the wave, that is power, okay, and divide it by the area, power of the wave divided by the area of the wave, and we get watts per meter squared, okay? That is the intensity of sound, watts per meter squared, okay? Now, what about for a spherical wave at its source? Well, it's a little bit different. We take the power of the source and divide it by 4 pi r squared. And notice that the intensity ratio at 2 different points, for example, if you were to go from here to here and look at the intensity ratio, notice it is the intensity at point 1 over intensity at point 2 is equal to the radius at r2 squared divided by the radius of r1 squared, okay? And it actually almost comes into the inverse square law a little bit, okay? We get into the inverse square law. Notice that right there. That's 1 over r squared. Light behaves similarly too, okay? All right, so, and I hope you wrote that formula down. Now, what about loudness of sound? Well, loudness of sound, in other words, what we talk about is decibels. When you have a intensity of a factor increases the sound, increasing the sound intensity by a factor of 10 results in an increase in perceived loudness by approximately 2, and we call this a sound intensity level. And by the way, this is a logarithmic scale, and so the threshold of hearing, in other words, the the lowest intensity that a normal human hearing is 1 times 10 to the negative 12th watts per meter squared. That's the threshold or the initial intensity, or I say initial intensity, threshold. In other words, that's the lowest intensity that humans can hear. But how do we find then the sound intensity level in what we call that Greek letter beta there? It represents decibels for any particular sound. Well, notice it is what? It is 10 dB. In other words, the log of what? I over I naught, or I initial, to find the actual intensity of sound, okay? In decibels. Decibels is the sound intensity level, okay? Not the actual intensity, a little bit different. There's a difference in intensity and intensity level, okay? Please note these equations, all right? So, the threshold of hearing corresponds to 0 decibels. In other words, you can't hear any lower than 0, right? That's common sense, isn't it? Okay? Now, if we take this and apply it to our equation, we find this equation, that the final intensity is equal to the initial intensity to the power of 10B over 10 dB, okay? And that's how we would find that. Here are some various threshold or various objects on the decibel scale. Notice, of course, what we can and can't hear start at 0, and that's the intensity in watts per meter. Then at 10 decibels, person breathing at 10 meters, a whisper, a quiet restaurant, normal conversation, busy traffic, rock concert, okay, all right, rock concert, a jet airliner is on here somewhere, I thought it was. No, it's not. A jet airliner is actually probably somewhere right around here to here, okay. Threshold of pain is 130 decibels, okay. In other words, your ears are really going to start hurting there, okay? You go much beyond that and burst your eardrum, okay? All right, and again, this is just a review of our equations and what they apply to. All right.